In this section, we're going to talk about continuity of a function. Intuitively, a graph is continuous over an interval if you can trace the graph with your pencil and not hit a break. So if you look at this one here, I can walk along this graph and I'm not going to hit any hole, any asymptote, or any jump. Even though it's got points, you can still keep going. This is a continuous graph. Whereas if you look at this graph, if I walk along this piece, I hit a hole here, and then there's this jump. All right, so this graph right here is discontinuous. So we will develop a formal definition of continuity using the concept of limits. So let's build the formal definition of continuity by looking at several discontinuous graphs. In this graph here, we can see it's discontinuous right here. We know that the reason this graph is discontinuous is because f of a is undefined, as we can see by this empty hole right here. So we're going to say this graph is discontinuous at x is equal to a because f of a is undefined. So because of this, we can answer this question here. Therefore, what is a necessary condition based on what we know about this graph for a graph to be continuous at x is equal to a? Well, we can conclude that f of a must be defined, for one thing. So let's just say that f of a must be defined. Now let's look at this graph here, where we have a jump discontinuity. Does this graph meet the first condition that f of a is defined? Well, we can see that we have a filled-in dot here at f of a. So it meets the first condition that f of a is defined. Okay, filled-in dot, f of a is defined. Next question, explain whether the limit exists at x is equal to a. So remember, in order for the limit to exist, the limit from the left and the limit from the right must approach the same y value. As you can see, the left-hand limit and the right-hand limits are not the same y value. So that means the limit at x is equal to a does not exist. So the limit as x approaches a of the function f of x does not exist. That is because the left and the right-hand limits are not equal. So then we're going to ask ourselves, therefore, what is another condition which must be met for a graph to be continuous at x is equal to a? So basically, in order to prevent something like this, a jump discontinuity, the limit as x approaches a of f of x must exist. So here's another graph. We can see this one is also discontinuous. So we're going to ask ourselves, is the function in the graph defined at x is equal to a? Well, there's a filled-in dot, so yes, f of a is defined. All right, so we're going to say we have a filled-in dot. Does the limit exist at x is equal to a? So if we approach from the left and we approach from the right, we're approaching the same value. So we're going to say yes, the limit as x approaches a of f of x exists. The left and the right-hand limits approach the same value. Okay, so these two conditions are necessary for continuity at x is equal to a, but they're still not sufficient. Okay, one more condition must be met. What is the final condition? So if you look at this dot here, if this dot actually was down here filling in the hole, then you'd have a continuous line. So think about it that way. The limit has to exist, f of a has to exist, but they have to be the same number. All right, so that's the final condition. So we can write that mathematically. So we can say that like this. The limit as x approaches a of f of x must equal the function evaluated at a. If that's the case, then we're going to have a continuous graph. So let's summarize this. The definition of continuity at a point. A function is continuous at a point where x is equal to a if and only if the following three conditions are met. F of a is defined. The limit as x approaches a of f of x exists. And the limit as x approaches a of f of x is equal to the function defined at a. If these three conditions are met, then you have a continuous graph. If you look at this graph here, even though it's kind of a jumpy graph, all of these three conditions are met at all of these unusual situations here. At this cusp right here, the left hand and the right hand limits equal the same number, and we have a filled-in dot. Right here, at this same sort of irregular situation here, the left and the right hand limits equal one another, and we have a filled-in dot. Same situation here. So this is an example of a continuous graph. In this example here, we're asked to use the definition of continuity to determine if the function is continuous at x is equal to 2. So the first condition says that f of 2 must be defined. The problem is if I put 2 in right here, I'll have a 0 in the denominator. So f of 2 is undefined. So we can say, let's use our three dots. That means therefore. Therefore, f of x is not continuous, because the first condition is not met. Here's another example. We're going to use the definition of continuity to determine if the function is continuous at x is equal to 3. So looking over here, it says you have a little line right here, which means you're going to use this piece of the function to find the value of f of 3. So f of 3 is going to equal negative 3 squared plus 4. So that's negative 9 plus 4, that's negative 5. So f of 3 is defined. First condition is met. Now we have to check whether the limit as x approaches 3 exists. In order to do that, we need to find the limit as x approaches 3 from the left and the limit as x approaches 3 from the right, and determine whether those two numbers are the same. So for approaching from the left, the values of x need to be less than 3, which means this piece is the piece we want. So we're going to substitute 3 into here, and that's that same number that we're going to get here, negative 5. So it's approaching negative 5 from the left. Now from the right, this piece right here says all of the x values greater than 3 are going to be on this piece of the graph. So if we're approaching from the right, we need to use this piece here. So substituting 3 into that piece, I've got 12 minus 8, that's 4. So the problem is that the left-hand limit and the right-hand limits are not equal, so we have a jump. So the way that we're going to say that is that the limit as x approaches 3 of the function f of x does not exist. Okay, so therefore, 3 dots, conclusion, f of x is not continuous. Next example says use the definition of continuity to determine if the function is continuous at x is equal to 1. So we have another piecewise defined function. So the first condition says, is the function defined at f of 1? So f of 1, according to our function here, here's x is equal to 1. So f of 1 is equal to 2. So f of 1 is defined. Now let's check the limits and see if the limit from the left, so the limit as x approaches 1 from the left of f of x, and the limit as x approaches 1 from the right of f of x are the same number. Otherwise, there's a jump. All right, so let's figure out what the limit from the left is. So coming from the left, all values are going to be less than 1, so we need to use this piece here. So that's a polynomial. So I'm just going to substitute 1 into the polynomial, and I'll get 2 plus 1, which is 3. All right, so that's the limit from the left. Now the limit from the right, so we need to look for the part where the x values are bigger than 1, so that's this piece over here, another polynomial. So evaluate the limit by substituting 1 into the polynomial, and I get 3 again. So we can conclude here that the limit as x approaches 1 of f of x must be 3. All right, but we have a problem. The last condition, the last requirement, says that the limit as x approaches 1 of f of x must be equal to f of 1. So this is 3 and this is 2, so they're not equal. So our conclusion is f of x is not continuous. So let's add, since the question says at x is equal to 1, at x is equal to 1. Let's go back on that other slide and put that here too. At x is equal to 3. And right here, at x is equal to 2. Now let's review how we classify discontinuity. So we've done this already before, but let's use the formal words here. So the formal word for this type of discontinuity here is a removable discontinuity. Sometimes we call it a hole. This kind of discontinuity here is called a jump discontinuity, and this one here is called an infinite discontinuity. So these are our vertical asymptotes. Those are their formal names. So in this example, we're just classifying the discontinuities. We want to determine which of the 3 types we have. So with this first piecewise defined function, it's likely that we have a jump discontinuity if the left-hand limit and the right-hand limits are not the same value at x is equal to 2. So let's check that. So the limit as x approaches 2 from the left, so we're talking about x values being less than 2. This polynomial over here is the part of the function we're looking at. So that means we can just go ahead and evaluate the polynomial at x is equal to 2. So that's 4 minus 1, which is 3. Now for the right-hand limit, we want to look at the part where the x values are greater than 2, so that's this polynomial here. So we know we can just evaluate the polynomial when x is equal to 2, and that would be 4. So these two numbers are not the same. So when those two numbers are not the same, that means there's a jump discontinuity. So we have a jump discontinuity for A. Now looking at the second one, it's possible that we have a removable discontinuity if this x minus 3 will cancel. So we want to check and see what the factored form of the numerator is if it factors. So we can see that it does factor, so let me just do this quickly. I don't like to make the videos too long, of course. So this would be x minus 3, x plus 2. Alright, so I can see that I can cancel these two factors, and I'm left with just x plus 2. Alright, so that's a removable discontinuity there. And when that happens, you end up with the graph of the line with a hole in it. Alright, so this is a removable discontinuity. The last one here is a rational function because it's a ratio of two polynomials. And we can see that if we put 4 in for x, if x is equal to 4, then we have the condition where f of 4 is undefined. Okay, so now we know, since this is a rational function, that this is going to be a vertical asymptote, which is going to occur at x is equal to 4. We've studied these quite a bit in Algebra 2 and pre-calculus. So rational functions have vertical asymptotes for the undefined values from the denominator. So when that occurs, we say this is a infinite discontinuity. So those are the names we're going to use for those, and that's what you'll see in your homework. So some functions are continuous over their entire domain. Okay? You'll not need to pick up your pencil while tracing the graph of these functions over their domain. Remember that x values at vertical asymptotes and at negative numbers under a square root, in fact any even root, are not in the domain in the first place. Okay, so we're not even talking about the values that aren't in the domain in the first place. Alright, so a trig function here, these are smooth curves. So these are continuous over their entire domain. Polynomials are smooth curves. These are continuous over their entire domain. Rational functions are continuous over their entire domain. Radical functions are also continuous over their entire domain. So we know that about these types of functions, which can simplify some of our work. Now here I want to say, if you need to review the basic shapes of these types of functions that we talked about in prior courses that were prerequisites for calculus, at this point take some time to type in various functions and transform them in Desmos graphing calculator, which is very quick and easy to use for that, and explore those functions and make sure you understand what those shapes are. If you need a list of the kind of functions or anything like that, just let me know. I'll give them to you, and you just type them in and you make sure you understand what the shapes of these basic functions are. So that's a prerequisite for calculus, that you have knowledge of the basic shapes of the functions we learned in Algebra 2 and pre-calculus. So let's write the domains of these functions here in interval notation over which the function is continuous. Okay, so we said that polynomials are continuous over their entire domain. So the domain of a polynomial function is all real numbers. So this polynomial is continuous over the interval negative infinity to positive infinity, which is all real numbers. All right, b is a rational function. This rational function is going to have an asymptote where x is equal to 2. So x is equal to 2 is a vertical asymptote. All right, so we're not going to have, the function is going to be undefined for x is equal to 2. So 2 is not in its domain. So the way that we would account for that asymptote, we're going to go from negative infinity all the way to 2. and then break for the asymptote and pick up on the other side of 2 where all of those x values will be included in domain. So that's how you're going to write your domain. Looking at C, we have another rational function. So you're going to have to factor the denominator. And then we'll know where our asymptotes or our holes or whatever it is lie. So we've got x, x. So let's try 2 and 4, negative, positive. Okay, so none of those factors are going to cancel, which means I have 2 vertical asymptotes. So one will occur at x is equal to negative 2, and one will occur at x is equal to 4. So I'm going to have a split domain at both of those x values. So I can go from negative infinity all the way to negative 2, and then I split for an asymptote, take up on the other side of negative 2, go all the way to 4, split for an asymptote, and then go all the way to positive infinity in that direction. So I've got 2 vertical asymptotes for the rational function in C, and that's how I'd write my domain over which this function is continuous. Okay, D is a square root function. So what we know about square root functions is that in order to have real x values as part of the domain, we can't have a negative value underneath the radical. So we can say that x minus 10 must be positive or equal to 0. So if I solve for x, I'll add 10 to the other side. That says that x must be greater than or equal to 10. So in interval notation, we would use a square bracket for 10, and we go all the way to positive infinity. So that's the domain over which this function is defined, and it's continuous over its entire domain. Remember, a square root function has this kind of a shape here. It's a smooth curve. So that one's continuous over its entire domain, which is 10 to positive infinity. Okay, the last one has another square root function as a part of it, and it's got this vertical translation here on the end, but that doesn't play into the domain. The main issue with the square root function is that what you have underneath the radical is greater than or equal to 0, so that you don't have an imaginary number. I'm going to solve for x here, so I'm going to subtract 8, and then I'm going to divide by negative 2. Let's scoot it up a little. So that means x is less than or equal to, flip your sign, 4. All right, so if x is less than or equal to 4, so if it helps to look at it on a number line, here's 4, you're going that way. So the way that I'd write my domain would be negative infinity to positive 4 square bracket. So I'm continuous over that entire all of those x values. So what that means is my square root function is pointing in this direction. And if you'll recall, and this is something you can explore on Desmos, like I was mentioning, if you have a negative x under the radical, that causes a reflection about the y-axis. That's why this one, which has a positive x, is facing in this direction, and this one, which has a negative in front of the x, is facing in this direction. That's because that negative caused a reflection about the y-axis. All right, so this is our domain over which this function is continuous. So the last thing that we need to talk about in this unit on continuity is called the intermediate value theorem. So this theorem says, let f be continuous over the closed interval AB. Here's A, here's B. So this section of the graph we're saying is continuous. No holes and jumps, none of that. if z is any real y value between f of a and f of b, so here's f of b. My graph is chopped off, so it's not lined up properly. And here's f of a. So we said z is any real y value between f of a and f of b. So somewhere in there, and here it is right here. Then there is a real x is equal to c value, real number x is equal to c, in this interval a, b. So here with this value c, which is an x value, lies between a and b, where f of c is equal to z. So it's another way of saying that this point right here has the coordinates c, comma z, or you could say c, comma f of c. So we're guaranteed basically to have a point between a f of a, which is this point here, and b f of b, which is this point here. So it's just a fancy way of saying if you have two endpoints of a continuous section of a graph, you're guaranteed to have some point lying on the curve in between there. Okay? So if you're guaranteed to have one point, you're guaranteed to have any point lying along here that has a value x from here, between here and here, and its corresponding y value. So all of these points are guaranteed to exist between this point and this point. It's just a fancy way of saying that. So this theorem is useful for finding unknown x-intercepts of a function. If a is a positive number, this one here, and b, this should say, hold on, that was a typo. If f of a is a positive number and f of b is a negative number, then somewhere the function crosses the x-axis in that interval between a and b. So what that's saying is that, let's say this point here, b f of b, is not up there but down here somewhere. So our graph could look something like that, let's say. If that's the case, we know that it had to have crossed the axis at some point in there to get from positive to negative. So that's how we can determine whether we can conclude at least whether a root or an x-intercept lies between 2 points on a continuous graph. So this example says determine when you can apply the intermediate value theorem. A says if f of x is continuous over the interval -2 to 5, and f at -2 is negative, and f of 5 is also negative, what conclusion can we make about the existence of zeros in the interval -2 to 5? Let's just see if we can visualize what's going on here. So at -2 and 5, we're talking about some continuous function existing. And it says here that f of -2 is negative. So we've got a negative y value at x is equal to -2. It also says f of 5 is negative. So we have a y value that's negative at f of 5. And we're asked, what conclusion can we make about the existence of zeros in the interval -2 to 5? Well, it turns out this is inconclusive with regard to zeros, because we don't know for sure that it crossed the x-axis. It could cross the x-axis and come back down, or it could completely stay on this side of the axis. We just don't know. So we can't make a conclusion whether or not there's zeros in that interval between -2 to 5. So we cannot conclude that the graph crosses the x-axis when all we're given are 2 points that have the same sign. So let's look at B. It says if f of x is continuous over the interval 3, 6, and f of 3 is greater than 0, which means f of 3 is a positive y value, and f of 6 is less than 0, which means f of 6 is a negative y value, what conclusion can we make about the existence of zeros in the interval 3 to 6? So let's do a visual. So we've got 3 and we've got 6, and we're told that our graph is continuous between 3 and 6. We're told that f of 3 is positive, so somewhere up here, and f of 6 is negative, so somewhere down here. And we're asked what conclusion can we make about the existence of zeros in 3 to 6. Well, one thing we know is that somewhere in there, in order to get from here down to here, it had to have crossed somewhere. Now, it could have gone up and down several times between 3 and 6, but we know it at least had to cross in one place. So we can make some kind of conclusion about zeros right here. So we can say, so our conclusion says the graph must cross at least once. A zero exists in the interval 3 to 6. Here's our last example using the intermediate value theorem. So if we look at this table of values, we're asked to determine the intervals in which a root must lie. So remember, we're looking for sign changes for the y values. If your sign goes from positive to negative or from negative to positive, then it had to have crossed over the x-axis in order for that to happen. And that means there's at least one root in that interval. Here we're going negative, negative. It's not crossing the x-axis, no sign change. Between 10 and 15, though, we're going from negative to positive. All right, so there's got to be a root in here. All right, so going from here to here, positive to positive, going from here to here, we've got a cross to go from positive to negative, so there's got to be a root in here. And then once again, I see another change in signs, and going from negative to positive, there's got to be a root in here too. All right, so the intervals in which a root must lie are 10 to 15, 20 to 30, and 30 to 40. Okay, so notice that I pop back and forth between using root, zeros, and x-intercepts quite a bit. It's because they all mean the same thing. These are places where the graph must cross the x-axis. They're also called solutions. All right, so we've taken care of all of the examples for the section here on continuity. You should be ready to try your homework problems. Let me know if you have any questions.